Wastewater engineering. Indices of self-purification. The stage of self-purification process can be determined by physical, chemical and biological analysis of the water. Color and turbidity are physical indices, while DO, BOD and suspended solids SS are the chemical indices which can mark the stage of purification. The oxygen deficit of polluted river stream. The oxygen deficient D at any time in a polluted river stream the oxygen deficient D at any time in a polluted river stream is the difference between the actual DO content of the water at that time and the saturation dissolved oxygen content at the water temperature, that is oxygen deficient is equal to saturation dissolved oxygen minus actual dissolved oxygen. In order to maintain clean conditions in river stream, the oxygen deficient must be nil, and this can be found out by knowing the rates of deoxygenation. Deoxygenation curve. In a polluted stream, the dissolved oxygen content goes on reducing due to decomposition of a volatile organic matter. The rate of deoxygenation depends upon the amount of organic matter remaining to be oxidized at the given time, that is LT, as well as on the temperature of reaction, that is T. Hence at a given temperature, the curve showing depletion of dissolved oxygen with time, that is deoxygenation curve, is similar to the first stage BOD curve. Reoxygenation curve. In order to counterbalance the consumption of dissolved oxygen due to deoxygenation, the atmosphere supplies oxygen to water, and the process is called reoxygenation. The rate at which the oxygen is supplied by the atmosphere to the polluted water depends upon the depth of receiving water. Rate is more in shallow depth. The condition of the body of water, rate is more in running stream than in a quiescent pond. The amount of dissolved oxygen which will be present in the water if it is fully saturated with the oxygen. The normal saturation dissolved oxygen value for fresh water varies between 14.6 mg per liter to 7.6 mg per liter for temperature varying between 0 degrees Celsius to 30 degrees Celsius. The saturation deficit or the oxygen deficient, that is the deficient of dissolved oxygen below the saturation value, and the temperature of the water. Depending on these factors, the rate of reoxygenation can also be expressed mathematically and plotted in the form of a curve called reoxygenation curve. Oxygen sac curve in a river receiving the discharge of sewage. Time of flow T days from point of pollution. Dissolved oxygen percent saturation. This one is the curve. This is curve first. Deoxygenation curve is equal to deoxygenation curve or curve showing depletion of dissolved oxygen in the absence of aeration. This is the reoxygenation curve, that is dissolved oxygen content supplied. Ordinate AB is equal to CD. Ordinate AB is equal to CD. That is, this ordinate AB is equal to CD. Ordinate AB is equal to CD. AB, CD. A, B, C, D. A, B, C, D. A, B, C, D. A, B, C, D. This one is a deoxygenation curve. First is your deoxygenation curve or curve showing depletion of dissolved oxygen in the absence of aeration. This one is the curve second, which is a reoxygenation curve, that is dissolved oxygen content supplied. Then curve third is equal to oxidation sac curve or oxygen deficit curve, that is the actual dissolved oxygen content or oxygen balance. This one is the critical point. This is the minimum oxygen balance. This is the maximum or critical deficit dissolved oxygen. Here the time of flow T days from point of pollution. Here the dissolved oxygen percent saturation. This is 0, 25, 50, 75, 100. Oxygen deficient curve. In a running polluted stream exposed to the atmosphere, the deoxidation as well as reoxidation go hand in hand. If deoxidation is more rapid than the reoxidation, an oxygen deficit results. Note: if the dissolved oxygen content becomes zero, aerobic conditions will be no longer be maintained and putrefaction will set in. The amount of resultant oxygen deficient can be obtained by algebraically adding the deoxidation and reoxidation curves. See curve third, figure 8.2. The resultant curve so maintained is called the oxidation sag curve or the oxygen deficient curve. So on this curve, the oxygen deficient D and the oxygen balance, that is 100 minus D percent in a stream after a certain lapse of time, can be found out. It can also be seen that when the deoxidation rate exceeds the reoxidation rate, the oxygen sag curve shows increasing deficient of oxygen. But when both the rates become equal, the critical point is reached, and then finally when the rate of deoxidation falls below that of reoxidation, the oxygen deficient goes on decreasing till it becomes zero. The entire analysis of superimposing the rate of deoxidation and reoxidation have been carried out mathematically, and the obtained results are expressed in the form of Streeter-Phelps equation, that is dt is equal to kd into L over kr minus kd into whole 10 raised to power minus kdt minus 10 raised to power minus krt into plus d naught into 10 raised to power minus krt, where dt is equal to dissolved oxygen deficient in milligram per liter after 3 days. L is equal to ultimate first stage BOD of the mix at the point of waste discharge in milligram per liter. D naught is equal to initial oxygen deficient of the mix at the mixing point in milligram per liter. Kd is equal to deoxidation quotient for the waste water, which can be expressed as equal to BOD rate constant determined in laboratory through BOD tests performed at different times on BOD bottles. I discussed in article 7.4.1.9. Also, Kd varies with temperature as per equation 7.18 as Kd T is equal to Kd into 20 into 1.047 into temperature into raised to power temperature minus 20. The typical values of Kd 20 vary between 0.1 and 0.2, generally taken as 0.1. Kr double star is equal to reoxidation coefficient. For the stream, it can be determined by the field test by using the equation Kr 20 star is equal to 3.9 into under root V over Y raised to power 1.5, where V is equal to average stream velocity in meter per second, Y is equal to average stream depth in meter. Kr varies with temperature as per the equation. Kr capital T is equal to Kr 20 into 1.016 into raised to power temperature minus 20, where Krt is the Kr value at T degree Celsius and Kr 20 is the Kr value at 20 degrees Celsius. Deoxidation coefficient for a river is in fact a little more than the BOD rate coefficient, since the BOD is exerted more rapidly in a river stream than that in the BOD bottle due to turbulent mixing river. However, for practical purposes, the value is to be taken to be the same as determined in the laboratory. Certain authors use Ks as a symbol for this constant. Values of reoxidation coefficient Kr at 20 degrees Celsius. Type of water body. Value of Kr 20 per body. Small ponds and backwaters 0.05 to 0.10. Sluggish streams, large lakes and impounding reservoirs 0.10 to 0.15. Large streams of low velocity 0.15 to 0.20. Large streams of normal velocity 0.20 to 0.30. Swift streams 0.30 to 0.50. Rapids and waterfalls over 0.5. The oxygen deficient curve can be plotted easily with the help of the equation 8.3 by using different value of T in days. This is the equation 8.3. The critical time Tc after which minimum dissolved oxygen occurs can be found by differentiating equation 8.3 equating it to 0, which on solving gives Tc is equal to 1 over Kr minus Kd into log whole Kd L minus Kr d naught plus Kd d naught over Kd L into Kr over Kd, and the critical or maximum oxygen deficit is given as dC is equal to Kd L over Kr into 10 raised to minus Kd into Tc. The constant Kr by Kd is sometimes represented by F, called self-purification constant, the values of which are given in the table 8.5. The values of a self-purification constant F is equal to Kr by Kd. Type of water body: small ponds and backwaters, value of F 0.5 to 1.0. Sluggish streams, large intakes and impounding reservoirs 1.0 to 1.5. Large streams of low velocity 1.5 to 2.0. Large streams of normal velocity 2.0 to 3.0. Swift streams 3.0 to 5.0. Rapids and waterfalls over 5.0. Tc is equal to 1 by Kd into F minus 1 into log 1 minus whole F minus 1 into d naught by L into F. From this equation dC is equal to Kd into L over Kr into 10 raised to minus Kd into T. dC is equal to L by F into 10 raised to minus Kd into Tc from the equation 8.7, that is this equation. Then log dC is equal to log L by F minus Kd into Tc. Then substituting the value of Tc from the equation 8.8 in the equation 8.10, we get from this equation, substituting the value. Then log dC is equal to log L by F minus Kd into 1 over Kd into F minus 1 into log F into 1 minus F minus 1 into d naught by L. Log dC is equal to log L by F minus 1 by F minus 1 log F into 1 minus F minus 1 into d naught by L. Then into F minus 1 log L by F minus log dC is equal to log F into 1 minus F minus 1 d naught by L. Then log L over F by dC raised to power F minus 1 is equal to log F into 1 minus F minus 1 d naught by L, or L by dE into F raised to power F minus 1 is equal to F into 1 minus F minus 1 into d naught by L. This is the important first stage equation in which L is the BOD of the mixture of sewage and steam, and F, Kd and Kr also corresponds to the temperature of the mixture of sewage and steam at outfall. The above equations are of practical value, help in preceding the oxygen content at any point along a stream, and thus helps in estimating the degree of waste treatment required, or of the amount of dilution necessary in order to maintain a certain dissolved oxygen in the stream. The few examples showing the use of this equation have been solved below.